We present Strivec, sparse trivector radiance fields. Recent work TensorF proposes two different ways to globally decompose the tensor volume into low-rank bases. One is global CP, which decomposes the tensor volume into three axis-aligned vector bases. The other one is global VM, which decomposes the tensor volume into three vector and matrix bases. If we compare CP with VM, we will see that vector bases from global CP decomposition have fewer parameters but lead to compromised quality. More components and parameters are usually needed to better fit a scene. However, a high-rank CP tensor is extremely hard to optimize, requiring unaffordable large computation and runtime memory costs for fetching and storing the features per rank and per array point. While VM decomposition, on the other hand, usually has better quality and easy to be optimized, but is intrinsically higher rank and has more parameters by involving matrix bases. Both CP and VM decomposition do parameter sharing among empty space and scene region, which is neither efficient nor scalable. To avoid these issues, we firstly initialize a coarse geometry from input images. The initial geometry is not limited to any specific method. It could be RGB alpha volume or MVS point cloud. We take RGB alpha volume for example. Instead of using global tensor bases to decompose the entire volume, we distribute multiple local tensors into the scene region according to the initial geometry. And then CP tensor decomposition is achieved within each local tensor. Here, the reason of not using VM decomposition is that CP indeed has a hard time representing the variation of a full scene, even with a large number of components. But CP decomposition within only a local region has enough rank and benefit from its compactness. Please refer to our paper for more details and comparisons. Moreover, the size of the local tensors is tunable with a hyperparameter. In our case, we consider multi-scale tensors at the same time to take care of the geometry and appearance commonalities and exploit spatial coherence at multiple local scales. Here we take single scale for illustration. As a nerve representation, we begin with ray casting from each view in our trained set. On each ray, we uniformly sample points from near to far. And then we ignore the sampled points outside the local tensors. Note that any sample point might be covered by multiple local tensors. We will take all of them into account. After having the density and appearance features from local tensor decomposition for each sample point, we calculate the corresponding pixel color with ray margin. We repeat this process by multiple iterations and finally finish the rendering. When we consider multi-scale case, we firstly distribute multi-scale local tensors based on initial geometry. Within each scale, we apply CP decomposition to calculate the features. Here again, a sample point might be covered by multiple local tensors of the same scale. Therefore, we do neighbor feature aggregation to account for this. We then apply multi-scale feature aggregation to consider the features of multi-scale local tensors at the same time. Finally, we query each sample point with its features with a coordinate-based MLP to calculate the density and view-dependent color. To conclude, our main contributions are threefold. First, our representation is locally sparse and low rank, which is easy to be optimized with only few parameters. Second, by skipping most empty space, our method is more efficient and is scalable to the large scene. Third, we can achieve better rendering quality than global CP and global VM decomposition. Here are the experiments.